And so Professor Matteo Pasquali is the A.J. Artsuk Professor of Chemical and Biomolecular Engineering, Professor of Chemistry, and Professor of Material Science and Nanoengineering at Rice University. And he's also the director of the Carbon Hub, an initiative that he started a few years ago with industrial support targeted at advancing materials, manufacturing, and commercialization. He started at Rice University in 2000 with a program on soft materials, but then he quickly started focusing on especially carbon materials with different aspects of carbon material manufacturing and utilization. And today in particular, he will be talking to us about the use of carbon to decarbonize and get hydrogen for free. Matteo, thank you very much for accepting our invitation, and we look very much forward to your presentation. The floor is yours.
Matteo, thanks a lot for having me, and thanks Alfred, Mads, and Jiwong also for the invitation, and to all of you for being here. And so today I'm going to try to give you a little bit of a different perspective on carbon, what to do with carbon as a material, and also how the way we've been evolving seems to be actually converging with how CORC has been evolving too. So first of all, we all have the same goal. Basically, the problem we're facing is atmospheric carbon dioxide has gone to almost double the pre-industrial levels, and so we need to reduce atmospheric CO2. Now, a lot of climate solutions are being proposed. I mean, for example, there's industrial decarbonization. We know we need to reduce the emissions related to making steel, aluminum, cement, and chemicals. We need hydrogen. We need renewables. We need to lightweight our transportation systems to make them more efficient. We need to electrify. We need to figure out what to do with the fossil hydrocarbon industry. Do we shut it off, or is there a way to keep it going? We need to protect jobs, manufacturing, and of course, we need to capture CO2 from the air. Now, the problem is that these solutions are all linked. Let me give you an example. All the efforts in industrial decarbonization right now are presuming that either we capture the CO2 coming out of the processes, or we use hydrogen in place of carbon to run the chemical reductions that need to be run to reduce metal ore to metals. Now, of course, if we want to do hydrogen, we've got two routes. Either we do steam methane reforming, and then we have to do CO2 capture, or otherwise we put more pressure on renewables, not only to provide electricity to supplant the fossil power plants, but also to provide additional electricity to make hydrogen by water spitting. Interesting, for things that are not discussed much right now, electrification and lightweighting are actually putting massive burdens on industrial decarbonization, because we're increasing the use for materials like copper, like aluminum, and like carbon fibers, or both for electrification and lightweighting. This is aluminum and carbon fibers, and these materials have a significantly higher CO2 footprint than, say, steel, which is the incumbent in a lot of these cases. And so there are these conflicting drivers. Each proposed path is making our path harder. And then for CO2 capture, there's also a question is, what are we going to do with this capture of CO2? And can we continue to have viable economies as we do this? So it's a little bit like fighting a hydra. You try to cut one head off and another head pops up, right? And so what I want to talk about today is how we can use carbon as a material and take a carbon shot. This is a little bit in the US Department of Energy language of taking shots. And if we take this carbon shot properly, we can actually slay the hydra. Now, one thing that some of you will know very well is that what we have is not so much just that were emitting CO2 and there were no emissions before, but it's we perturb the natural cycle. And we cause about a 5% imbalance. And also the natural cycle is working a little bit harder right now because the concentration of CO2 is higher. So the reverse fluxes into land and oceans are higher than normal. And therefore, if we reduce emissions, we are sort of automatically starting to get some of that CO2 back in. Now, the other thing is that the problem of CO2 emissions, it's largely a problem of industrial, including building emissions. The transport is actually largely the easier problem to solve because we know how to electrify cars. And in fact, you see this issue of industrial emissions very much in how the CO2 emissions per country have reversed. United States and the European Union used to be the dominant emitters, and then once manufacturing switched to China, ended up, recently China surpassed the combined emission of the United States and Europe. And so the couple of messages here, and I think this is probably something that Alfred will reinforce: nature can help us. And the other one is making stuff causes CO2 emissions. Now, the next thing I want to talk is about the fossil hydrocarbon industry, that's which of course is responsible for the CO2 emission. What's interesting, almost all the emissions that come from hydrocarbons do not come from the extraction of the natural resources, but come from the use of the resource because we burn almost all of it. And so it's efficient, or to put everything in metrics. So oil is about 4.2 gigatons, natural gas is 2.5 gigatons. And if we look at how we move it through, about 95% of this goes as fuel. And so that's about a little over half than the CO2 emissions, about 19 gigatons. And a small amount goes in polymer, lubricants, and chemicals. And those have actually relatively low CO2 emissions associated with their production. Now, if we look at it in terms of mass, we have a situation, we have 5.5 gigatons of carbon that has an energy content of about 180 exajoules, and 1.2 gigatons of hydrogen, and that has an energy content of 1.170 exajoules. Pardon me for neglecting the delta H of formation of hydrocarbons from carbon and hydrogen, but that's small. It's less than 10% of the total. And so in a situation where we're still rely on coal, natural gas, and oil for most of our energy, there is a question, is there a way to actually split this stream and use the hydrogen for energy and use the carbon as material, right? Because this would actually give us a way to continue to provide for about half of the oil and gas energy, but also now use carbon productively. And so how would how does this work? Like, I mean, so splitting hydrocarbons is not new. Methane or natural gas has been split into its constituent in hydrogen and carbon for over 100 years. The oldest patents are from the early 1900s. What's interesting, if you look at the delta H of reaction, the minimum energy on the basis of a ton of hydrogen is 18.8 gigajoules. But the ton of hydrogen has 142 gigajoules of energy. And so it is a process that, even though it's endothermal, actually could be a net generator of hydrogen in terms of energy content. However, it's very skewed on the carbon. Even if we use methane, which is the hydrocarbon that has the highest ratio of hydrogen to carbon, we end up with 3 tons of solid carbon. But there's other things. Hydrogen is a commodity. As much as we give them colors, all the hydrogen is the same, and we may decide how pure it is. Carbon is inherently a specialty. Elemental carbon or carbon in the zero valence states exists in many, many forms, and most of them being amorphous. And so there's a question of what are we going to make and how efficiently, and what's going to be the cost, and what's going to be the policy that drives these projects. And also where are we going to put the carbon? Because if you look at the carbon black market, it's about 50 million tons a year, which is tiny compared to the numbers we had before of 5.5 billion tons. Okay, so clearly making carbon black can be a nice specialty way to use carbon, but doesn't go very far. All the other markets are small. Graphite, carbon fibers, and other markets are combining to a little over a gigaton. And the issue is that the cheaper grades like carbon black don't have structural integrity. So you can use them as filler, but you can't build big stuff out of it. And the larger stuff like carbon fibers have a high cost, high energy cost, and high CO2 footprint, and therefore they can't be used on a large scale because otherwise they become too expensive and too energy and CO2 intensive. So what could we do? What is it that we use a lot of materials? What are the opportunities? So this is a plot from a book by Ashby from Cambridge on how we use materials, and we put oil and gas here for reference. And we see there's a few areas, but one commonality is structural integrity is key for widespread use. So carbon black, for example, is about as cheap as steel, about $1 a kilogram, but is used in a very small quantity. Also look at the difference between polyethylene, polypropylene, PVC, which are all materials in the low $1.50 a kilo, and they're used at a scale that's almost 10 times or larger than carbon black. Of course, we don't want to displace construction woods. That's a great place to put carbon to use and store it for a long time. We could go over here. This is a really hard play because these are materials that have very low value in the order of 5 cents a kilo. For a baseline, natural gas is about 15 cents a kilo, fossil natural gas and oil about 60 to 80 cents a kilo. But this is where there is a huge opportunity, metals. Steels start at 80 cents a kilo and they go to $5 to $7 a kilo for high-end stainless and even higher for specialty. Aluminum is $2 to $3 a kilo. Copper, it's $7 to $8 a kilo. And also these are materials that are used a lot in transportation. That's how we build our car, for example. And therefore, their high density is a major liability. They're also big offenders in terms of industrial CO2 emissions. Steel alone is a big fraction. Copper is smaller just because of the quantity of copper that's made, but it's growing very fast. Aluminum is the most intensive, and cement, of course, is also a big offender. There's another thing that we should remember as we look at metals and other materials is this is the footprint of mining. These, for example, are recent deforestation and mining that's happening in the Amazon in Brazil, where vast lands, tracts are being clear-cut to mine bauxite, and the rivers are dammed to make hydroelectric power on site to reduce the bauxite to aluminum. And that environmental devastation is not captured just by the CO2 footprint. So we need to be very careful as we go towards an economy that may be using a lot more steel, a lot more aluminum and copper. So if we could basically eliminate these metals, we would automatically save 12% of the world energy. And then if we add in cement, it's about 16% of the CO2 emission. So Bill Gates always asks, what's your plan for steel? And our plan for steel is to replace it, right? So we're not going to do steel in a better way. We're just going to get rid of steel and replace it with carbon. And if we can do it with a lower energy use or comparable energy use, then we'll eliminate the CO2 emission because the carbon is going to be in the material. There's almost no steel in carbon, it's incidental, and there's certainly no carbon, sorry, there's almost no carbon in steel, and there's no carbon in aluminum and copper and cement. So what would the pathway look like? Well, you can think about using lots of different hydrocarbons or even alcohols. The delta H of reaction is relatively small. Methane is one of the ones that has the highest delta H of reaction per kilo of feedstock. And if we could split it, we would get hydrogen and carbon. But what's very interesting, in the last 30 years, a new class of carbon has emerged based on carbon nanotubes graphenes, and these are carbons that have structural integrity. So it's possible to take these, let's say, molecules and make them into usable shapes with room temperature solution processing. Normally this is what I do show and tell if I'm in person. On a webinar, I put there a sample. This is about 1.5 kilometers of carbon nanotube wire. And you see the size of the hands of the person that's holding. And this has conductivity and strength that are comparable to copper in terms of conductivity and steel in terms of strength. And then you need to find manufacturing methods to take these threads and make them into shapes and put them into large markets. So historically, there was a lot of promise for carbon nanotubes back in the 90s. However, the promise was based on looking at carbon nanotubes that are really molecules and attributing to them properties that normally we attribute to macroscopic materials, like strength is not defined for a molecule, it's defined for a continuum. And the same is true for electrical and thermal conductivity. And then there was a lot of disillusionment in the late 2000s and early 2010s that this field that promised a lot, but would never do anything. But in reality, the field kept growing, and as Matteo alluded, I was one of the people who kept working on this because I really believed in the promise. And now there are multiple companies that can actually make these materials on the kilo to ton scale and make shape factors that are quite attractive. So it's no longer a laboratory curiosity. Properties have gotten better. Back in the early 2000s, we could get a paper in Science with what I would call modest properties in terms of strength and electrical conductivity. Steel is somewhere around here at a gigapascal, but every few years, properties got better because we understood the science of this, and I'll tell you a little bit more about it later. And so by now, with this doubling every 3 years, we got properties that are really competitive with other materials, and the scale has gone up. We can make fabrics, etc. So in terms of properties, these materials don't have the best properties of any other material. These are Ashby plots of properties like strength and electrical conductivity, or normalized by mass. This is thermal conductivity and modulus. But you see that they're on the top right quadrant. And so they can compete with carbon fibers and other polymeric fibers in terms of strength, and they can compete with metals in terms of conductivity. Where they can't compete right now is cost. And the impact, if they could compete in cost and displace incumbents, it would be in the number of billions of gigatons of CO2. And this is just if you think about using fossil hydrocarbons. Okay, if we could use hydrocarbons that come from fixation of CO2 via biological or chemical routes, then there will be significantly higher CO2 emissions, because there will also be the effect of pulling the CO2 out of the atmosphere. So how does this work? Right now, these are flow-through reactors. They're catalytic reactors or catalysts. Precursors are injected in the reactors, or they are placed on catalyst supports, as Matteo Carniello does. And the typical reaction temperature are, let's say, in the ballpark of about 1000 C, a little lower for supported catalyst, a little higher for what's called floating catalyst. And then one has control to all the processes of catalyst, precursors decomposition, formation of a catalyst, nucleation of the nanotubes, all the way to the growth. And these were treated largely as black boxes. And it's only been in the last 5 years that there has been efforts to really understand what's happening in these reactors. And what's very important is one has to make the right material. If you don't make the right material, then even though you may be efficient, you haven't really solved the problem. This is what the reactor looks like at on. Here, the catalyst has just been turned on, and you see the formation of sort of like smoke, and that's coming towards us. Some of the advances recently that we're learning, also in collaboration with Sam and Kim KIST in South Korea and Adam Boyce at Cambridge, has been getting conversion and selectivity that are very high and high quality CNTs at the same time. So we're been estimating what the process efficiency here is. So to some extent, the metric here is the embodied energy. You want to make this material using an amount of energy that's comparable to the energy that's used to make incumbents like carbon fibers, aluminum, etc. And we started off this program, we were over here. And then ARPA-E funded us, and in parallel funded Matteo Carniello. And then about a year ago, we started getting over here, and in collaboration with KIST, we've been moving down here, and we're now at a level of 500-600 megajoules per kilo, which is very promising for something that's so early in the path. We think that a really big impact target will be if we get here at about 100 megajoules per kilo. So at this point, we would be levelized with some of the high-end steels, aluminum, and carbon fibers. Now, Huntsman, which has also been funded by ARPA here, can now go and make this material in a very efficient way, but they lost properties. And so now there is also a question of whether Huntsman can walk back up this line, give up a little bit of efficiency, and still get recover the properties. But the bottom line, one does not have to go to very high efficiencies to have an effect. If one can get a 5 to 10% reaction efficiency, this route becomes very interesting. Now, the next step is how to take this disordered material and make a fiber. And this is where my group has made most of their contribution in the last 20 years, which is by solution processing. So carbon nanotubes can be put in acids. They are natural acids, are natural solvents, and at sufficiently high concentration, they make a liquid crystal. We can then be extruded out of a spinneret, either a single hole or multiple holes, and forms a fiber. And then the liquid dope is coagulated by using a non-solvent that removes the acid, and we're left with a fiber. So that's how we make this. It's possible also to make foams, to make films, coatings, and tapes. How did we get the properties? It's very similar to what happens with polymers. If you want polymers in properties in polymers, you have to have longer molecular weight polymers. And here we found the same science. Initially, we were getting low properties because our molecular weight was low. The aspect ratio, which is the length of a nanotube divided by the diameter, was too low. But with time, we learn how to make longer and longer nanotubes. And these are not just my group, but it's a community. And my group was the one who really essentially established this scaling that you almost scale linearly, your properties almost scale linearly, both mechanical and electrical properties. And so as you make longer and longer nanotubes, you get higher and higher properties. This also affects your phase behavior, and we found out ways to use phase behavior and also rheology to measure, for example, aspect ratio. So what this has given us is the target. How do we measure whether the material is good, how good it is, what are the potentials? Now, another effort that we've had is to make fiber spinning more efficient. This is how we used to make fibers. Look how slowly this roller is moving. And now this is what we can do. So we sped up the process dramatically. And if you look at essentially efficiency, you want to go outwards in all of these characteristics. You want to have high properties, and then you want to have a high throughput of fibers, and you want to have the highest possible concentration of solids in your solvent. And we used to lose properties as we increase the concentration and throughput. And now we found ways to increase throughput and concentration and reduce cost while keeping the properties essentially the same. And this is also an area where, however, there is a lot of work that needs to be done, and it has to be done in parallel with the synthesis because the two interact with each other. Now, the last thing is, if you want to change the way materials are used, you need to work with the people who make structure. Always being Italian, I always use this example. This is a Ponte di Tiberio, was made about 2,000 years ago. In Rimini, it's still standing, people drive on top of it. It's made out of stone, and he uses the Roman arch structure, because in an arch, all your material is in compression, and it turns out that stone is very strong in compression and relatively light, actually. And if you had steel and you gave steel to a bridge builder who only knows to build arch bridges, they will look at your property and they will say, this is an inferior material, right? And then they would also say, how do I build this? You know, the Romans had stone cutters on site. You can't cut steel with the same tool, right? You have to, and then so you need, now this is actually a tribute to Matteo Carniello, right? This is what you have to do. You have to change the design of the bridge. And so when you go to a suspension bridge, that's where steel really shines, because a lot of the structure is in tension, and steel is very good in tension, whereas a stone is terrible in tension and bending. And therefore, you can make bridges that are much more efficient, even though your material would actually be worse if you made a stone bridge. Okay, so you have to coordinate with the people who make objects, not just stop making a material. So I talked a little bit about this path, and so how do we connect to other things and to what you guys are doing? Well, first of all, I mostly focus on a feedstock right now that comes from fossil sources. But of course, the feedstock could come from many other sources. It could come from captured CO2, it could come from waste biomass, waste plastics, and it is the reaction could make small molecule hydrocarbons or alcohols that can be used as feedstock. At this point, we get into circularity and also carbon negative processes, because we may be fixing CO2 into small molecules and then fixing the carbon in the small molecules into materials. In some cases, we get hydrogen, not so much if we're doing the CO2 route, but if we're doing the natural gas or oil route, we will get a positive hydrogen production. There's other uses for carbon that could go to very large scale, like amendment of soils, remediation of soil, for water purifications. And this can help with other pressing needs for natural resources, like need for water and need for higher agriculture. We may be able to affect the built environment and affect, of course, industrial decarbonization. Reduce mining. This is very important. Reduce mining and reclaiming land. It's a big deal. It doesn't affect us as much directly in the West, because most of the mining is down outside the developed countries. But this is certainly a big problem for a developing country. And we could use this material to power our new electrical infrastructures. And this is going to give us biomanufacturing jobs, chemical manufacturing jobs, mechanical and maker jobs, and supply chain security and resilience. I didn't redo this thing with the world map. Texas is big in this phase, but certainly it scales out already. So to organize this, we started something that's called the Carbon Powder here. It's made here at Rice University. The idea is really we need to create a field, because there's not that many people who are talking about using carbon on a very large scale as a material. And so we want to accelerate the emergence of this industry. We want to direct and fund research in the highest impact areas and foster the acceleration of companies. And it is designed to be very collaborative. We're collaborating with the federal government, agencies, national labs, and also we want to strategically collaborate with other leading academic centers. So right now, we're organized in two ways. One is we'd like to have members from all areas, from institutions are interested in making a feedstock, and all the way to organizations that are interested in using the carbon. We're funded industrially. We have funding from oil and gas companies, but also from cable manufacturer, electrical cable manufacturer, industrials, chemicals, etc. And we have a number of organizations who are participating, but it's built to be open and have others join us. Right now, we have about 3 million dollars of projects under contract. This is about a year and a half. About 2/3 of them are in the US, and about 1/3 of them are in Europe and South Korea. And so I think I'm kind of out of time. I'd like to thank my students, thank my founding members, and say, we will join forces with you with CORC. All right, thanks for your attention.
Thank you, Matteo, for the wonderful presentation and this plugin too.